Rapid advances in solid-state lighting and sensing have made possible the exploration of new scene capture techniques for computer graphics and computer vision. In this scene, a video projector is throwing a color wash over a moving cloth. 9 passive tags mounted on the cloth detect their position and orientation. This allows us to render a virtual label over the cloth. The tags also detect the color of incident illumination, allowing our label to match the color wash regardless of label color. Our tags can be hidden under clothing so that only their sensors are exposed. This means that actors can wear a final costume and be tracked under theatrical lighting or in a natural setting. A motor can rotate this arm so quickly that our camera cannot see it. We are able to accurately track the arm using the passive optical tags mounted at each end. Here, the tags capture their location 500 times a second. The key to our system are inexpensive solid-state projectors which can project 10,000 patterns per second. Shown here is the space labeling pattern from one projector. For illustration, it is 1,000 times slower than actual speed. The full speed pattern is projected using infrared light that is not visible to the human eye. This provides 10 bits of resolution in one dimension. By exploiting the epipolar geometry of a carefully configured cluster of projectors, we are able to generate 2- or 3-dimensional tracking data at 500 or 330 updates per second, respectively. Our system is much more portable than one using multiple cameras. Alternating flashes from 4 orientation beacons allow our tags to determine their orientation using an intensity-based technique. Here are examples of the orientation data recovered by tags. Our prototype tags have a PIC microcontroller, flash memory, and optical sensors that detect their location, orientation, and the color of incident illumination, which cannot be captured by other marker-based techniques. As the tags are completely passive, their number is limited only by the physical constraints of the capture volume, and the system retains the same speed regardless of how many tags are in operation. When a tag scene is imaged with an external camera, we can factor in the radiance measured at the corresponding camera pixels and the incident illumination detected by the tag to determine the intrinsic reflectance of the scene and correct for colored ambient illumination. It should be noted that our projectors are capable of projecting millions of patterns per second. With an appropriate receiver, this system could easily run at megahertz rates. We can achieve one-dimensional update rates of over 500,000 samples per second should the need for such high speed arise. In the near future, light sources used in movie and television studios, conference rooms, offices, and even homes will be based on solid-state technology. These fast-switching light sources naturally lend themselves to applications beyond simple illumination. We have presented a scheme in which the modern solid-state light source can be used to estimate useful information about points in the environment. We hope that promising technologies such as light-sensing fabrics for dense sampling, radio frequency identification transceivers for batteryless tags, and optical CDMA for uninterrupted space labeling will further stimulate techniques based on scene point photosensing.